Okay, in this episode, we will solve a transient problem via the implicit scheme. The explicit scheme has already been explained in the official length in the lecture series by the school, but I'm going to go through the implicit scheme here in this tutorial. So, like I said, we're solving a transient problem. Transient problem means that the values of phi vary with time. So before this tutorial, what we see were steady state problems. Steady state problems. So steady state means d phi dt is equal to 0. It means it doesn't change with time. Okay, this thing means it doesn't change with time. So what we will see is, for example, on a phi versus x graph. Okay, on a phi versus x graph, it will just be stuck like that, even at time equals to 1, or even at time equals to 1, or time equals to 2, or time equals to 3. Your phi versus x graph is just stuck at this shape. But in a transient problem, okay, in a transient problem, then there will be d phi dt. Okay, d phi dt will show up in the governing equation, in the transport equation. So d phi dt will show up. It doesn't have a value of 0. And what you'll see is that the phi versus x graph will change over time. Okay, it's now transient. This is what you call transient. So transient means it changes over time. So it wouldn't be like, for example, a bar at some stuck fixed temperature profile. It would actually like cool down or heat up if phi represents temperature. Okay, if phi represents temperature. Of course, phi can represent concentration and momentum. But let's just use temperature as an intuitive special case, okay, as an intuitive example. So, for example, in a transient problem, if I look at time equals to 1, maybe the graph would look something like, like this. And then maybe at time equals to 2, then maybe the graph will like lower down like this. And then maybe at time equals to 3, it changes yet again. So, if you look at a phi versus x graph for a transient problem, it would look like a video. Yeah, you actually see the graph. Whereas for a steady state problem, which we faced so far before this tutorial, right? You never see d phi dt show up. Okay, so that means it's a steady state problem. So for a steady state problem, even at time equals to 1, even at time equals to 2, even at time equals to 100, even at time equals to 100,000, it would just be stuck at that initial shape that you see. Okay, so in the implicit scheme, we're going to we're going to solve for solutions of phi, not only for how they vary with x, but also how they vary with time. Okay, so let's just get into the important formulas that we need for solving transient problems for the transport equation. Okay, so important formulas. Now we have three important formulas that we need to know. Three important formulas. So the first two formulas are related to integration with time. So let's draw a time, okay, phi versus time graph. So the the y-axis, okay, let's not say phi. Let's just take a general function f, okay, a general function, any general function. So let's say we have this piece of curve. It's a very tiny segment of a curve, but I'm just zooming it in. Okay, then we have an initial time, and then delta t seconds later we have this value. Okay, so this time segment is delta t long, and then after that, this endpoint here is at delta t. Okay, so this function is given by f of t, right? So that means over here at t equals to 0, this will be f of 0. And then over here, when t equals to delta t, that means this point is given by the value of f of delta t. Okay, so I think that's all cleared up. Now, what do we have to know? We have to know these two approximations. So one approximation is this. So you're most likely going to encounter this kind of integral in solving transient problems. How do we go about finding the value of these of this integral, okay? Because one thing to know is, okay, let's get clear of what these terms are. So this is at initial time, right? It's initial time because this happens at time equals to 0. It's at the very start of the problem. But for in a general case, we consider this to be the past, a past data in time. And then this would be a future data in time. Okay? A past and a future data. So usually past datas are known because they happen and then we know what they are. We can measure what they are. They happened already and then we can measure what they are. So this is usually known. This is a known value that we can measure. And of course, we are most likely going to know the initial conditions of a problem, right? Like before the experiment starts, okay, we can measure this phi to be in what distribution. So usually initially the phi distribution is known, okay? And likewise, we can extend that to saying past data are actually known, okay? So they already happened, we already collected data about it, so usually past data are known. Future is unknown, right? Because we can't exactly predict the future, so to speak, okay? But that's what the solving transient problems are about. We're trying to use the past data and then try to calculate and make predictions for the future. And usually the future is unknown and we use the past data to calculate for future data. So we don't know, let's say, because the problem in transient problems is that this, we don't know what the value of phi is at time equals to, let's say, 40 seconds, or we don't know what the value of phi is at time equals to 80 seconds. So what we're going to do is we're going to use our initial conditions and eventually calculate, whatever time you need. If I need time equals to 40, then I'll calculate for that. If I need time equals to 80, then I'll calculate for that. Okay? But for the purposes of this course, in final examinations, what we are required to do is obtain a system of equations to to enable us to calculate these values. So we're not actually going to calculate the values at, okay, time equals to 40 or time equals to 80, but we're going to obtain a system of equations which will help us get this. Because this system of equations is like a machine. Okay, let me just plot this out. We create a system of equations, a system of equations, which helps us get our machines. So let's say as a scientist, I want, okay, I want to know what the value of phi is, at time equals to, let's say, 100 seconds. So I'll input this, and then out comes some value. Okay, the idea is basically like this. It's not entirely accurate, but I hope I can convey this idea. So what we're interested to do is building this machine. Okay, so in a final examination, we want the system of equations. That's all what is required of us. So let's get building. Okay, so we have some past data. Okay, just be clear, I meant the word data. Okay, in case our accents are different, we have some past data and future data. We usually know what the past data is. We don't know what the future data is. We want to calculate for it. And to do that, we will create this system of equations, which is required here. So in this tutorial problem, Professor Shu wanted you to actually get the solution, but I'm just going to go with the normal standard route of how they ask things in the finals, and that is to obtain the system of equations. So let's take this as our objective of this tutorial. Okay. Okay. So where was I? So we want to know how to evaluate this integral, and there are two ways to do it. Let's take these two alternatives. So one way is we use this formula. So we have f of delta t multiplied by delta t, and another way is this. So same thing, I want to calculate this, but another alternative is this. So f of 0 times delta t. So let's have an idea of where we're going. Let's take a look at this integral alone. What is the physical meaning of this on the f versus t graph? The integral of a graph is the area under the graph, right? The area under the graph. And most of us will know this by now. So the question is, how would you approximate this area under the graph? And there are two ways to go about it, which I've explained, which I've shown in this formula, in these two formulas here. So Let's have a look. What is f of delta t? F of delta t will be this height, correct? And then what is delta t? It's the size, it's the length of this segment, correct? It's the length of this segment which I have shown here. So if you take this height times this segment, wouldn't that be the area of this rectangle? I'm sure you will agree, right? It will be the area of this rectangle. And that is one way to approximate it. But you notice there's some uh excess area which you didn't account for. Okay, so keep in mind that this is an approximation. Okay, now it's important to know the name of these two formulas, or they're not the names of these formulas, but they're formulas in which we use when we do the. So for this case, this will be the implicit scheme. Okay, and of course, the second formula is the one which you use for the explicit scheme. Now, let me explain why this is the case. The implicit scheme, okay, the word implicit means indirect, right? The word implicit means indirect. So, in what sense is it implicit? Okay, in what sense is it indirect? Let's have a look. Okay, let's investigate the explicit scheme to contrast first. The explicit scheme, instead of using this height now to calculate the area of the rectangle, instead, what they will use is this height and then multiply by this delta t to find the area of this rectangle. Okay, so this is another approximation for the area under this graph, right? The integral f of t from 0 to delta t. So let's have a look closely at this side now. F of delta t is this. And what did we say earlier? This is unknown, right? This value is unknown. We don't know what f of delta t is. Okay? So, take a look at this. This is unknown, but you're using it to calculate this integral anyway. Somewhere along the governing equation, we're going to perform this integral. And this integral will eventually, sorry, this equation that we're doing will eventually give us the system of equations. Okay? Okay, so let me write down what's our flow of ideas. So we always start with a governing equation, right? So we always start with the governing equation, which is the transport equation, governing equation, right? So this flow follows the general flow of how we solve problems up to this point in the previous tutorials. You can check that out if you haven't. So we always start with the governing equation. Then if we use FVM, the finite volume method, we always involve some integral, right? At first, we only integrate with respect to space. This time, we're going to involve integration with respect to time, okay? And when we do integration with respect to time, we're going to involve either of these two formulas, depending on which scheme we take. So if we use the implicit scheme, we will use this formula. If we use the explicit scheme, we will use this formula. Okay? But here's the funny thing. We want to know future values of phi, right? We want to know future values of phi. But how can we use an unknown to find an unknown in the future? And this is, in a sense, how it may be implicit. Okay, it's indirect. We use an unknown to eventually find an unknown. It's possible. Take my word for it. It's possible, and that's why it's implicit. It's not a very direct way of doing it. Whereas the explicit scheme is a direct way of doing it. So you can check out the elaboration in the lecture, because I'm not gonna go through here. It's a bit too lengthy for my elaboration. Yeah. But the implicit scheme, you use a known, right? Okay, so let me label this for annotation. So this is a known. It's a known value. It's a known value. So using this known value, you can directly calculate the next time step. Okay, so delta t is called time step. It's the smallest skip in time that you're gonna see. So what do I mean? It's basically a resolution in time. For example, I'm sure you've seen these old fashioned films before, right? Films like this, which are really long. Yeah. And then you require a projector, and then it's like the film would like go through, and then you have a projector. So let me hold on. Let me go find an image of this. So I'm pretty sure many of you might be familiar with this kind of old fashioned film in back in the 90s, 60s, in the 60s. Yeah. So the faster these films move, right, through the projector, because there's a light that will shine through these films, the faster that these films move through the projector, the smoother your image feels. Now let's consider this. Take a look at my hand. When I wave through at the camera, okay? The way I can make an image using this kind of old-fashioned film is by taking a picture at this time and then moving it a bit, and then taking a new picture and then moving it a bit, and taking a new picture and moving it a bit. So what would you see? You would see something like tick 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 tick, and then tick 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 tick, something like that. But if the time step is smaller and smaller and smaller, it will look smoother. Like if the time step was like, let's say 1 second, okay, you will see like this: 1, 2, 3, 4, 5, 6, which is very unsmooth, right? But if the time step is smaller, let's say half a second, then maybe it will look like something like this. But if it's even smaller, it would look smooth. Okay, so to make your transient problems more accurate, you can decrease the time step, and that's what this delta t is. It's a time step. Okay, so it's how you refine your mesh in time. Okay, so let's get back to the idea. Okay, yeah. So using a known value, you can calculate future times at many time steps. Okay, so that's the plan. Yeah, that's the plan. So the explicit scheme is easier comparatively compared to the implicit scheme. The explicit scheme, sorry, I think I misspoke. The explicit scheme is easier than the implicit scheme, which has been gone through in the lectures. So in this video, I'm going to go through the implicit scheme. The implicit scheme. See? So let's work that out. So we're not done yet. Like I said, I promised you 3 formulas. So these are the first 2 formulas. One is the implicit scheme, where we use an unknown to find future unknown values. And we have the explicit scheme, which we use a known value, the initial condition. Okay, right? This is at time equals to 0. So this is the initial condition. You use a known value to find unknown future times. Okay. And now we're going to look at another approximation, which is related to space. Okay, now we're looking not at the variable t, we're going to look at the variable x. So let's consider another curve like this. So now this is a curve of f of x. Okay, this is a graph of f of x. Okay, so let's say this variable is the x, and this is at position x equals to a, and this is at the position x equals to b. Okay, okay, so this is f of a, and then this is f of b. Okay, so now we want to find the integral from a to b f of x with respect to d of x. I mean dx, which is this graph, correct? Yeah, which is the area under this graph. So the way we do this, the most accurate way we do this is using this formula. F of a plus b over 2 times b minus a. Okay, let's have a look. What is b minus a? This is more obvious than this other term. B minus a is the length of this segment. Okay, I think a lot of you agree with that. But what about f of a plus 2? I mean, f of a plus b over 2. Let's take a look. What is a plus b over 2? A plus b over 2 is the point right, exactly right in between a and b. Okay, so directly in the middle of a and b is this point, which is a plus b over 2, right? So that means f of a plus b over 2 would be the corresponding f value at this value of x. So if I go up, this is f of a plus b over 2. Okay, so that means we take this y value, we multiply it by a plus b over 2, And so we get this graph. I mean, this shaded area. Yeah, yeah, which is more accurate than the other two versions of this integral. Okay, but take note, when do you use these three formulas? Okay, so it's important to know. You will only use these three formulas. Okay, so let me put a note here. Only use the above three formulas when you cannot use integration to downgrade derivatives. Now, what do I mean by downgrade derivatives? Okay, this is a term that I made myself. Okay, what does it mean by to downgrade a derivative? Okay, let's say I give you, for example, dt dx. Okay, and now I ask you, okay, integrate this term with respect to x. I think it's obvious to you that, okay, integration is the opposite of differentiation. So these two effects will cancel, right? So the integral will cancel with the derivative. So I'm only left with t, right? I'm only left with t. So my answer will be t. Okay, this will be my answer. And this is what I mean by downgrading the derivative. I see an integral, I see a derivative, the integral will downgrade the derivative back into the original function. Now let's have another example. Let's say I give you d square phi d t square. Okay, and now I ask you to integrate with respect to uh time. Okay, this is the second derivative, and this is an integral. Integrals and derivatives are opposite effects, right? So the integral will cancel with one of the derivatives, right? This is the second derivative. So actually it's differentiation of the differentiation. So this integral will cancel with one of the derivatives, and what I'm left with is just the first derivative. See? So this is what I mean by downgrading. At first, it was the second derivative, and then we had the integration. It kills one of the derivatives, and now we went from second derivative and we downgraded back to the first derivative. We downgrade it back to the first derivative. So let's say I want to integrate this again. Okay. So you see, integrals are opposite effects of derivatives. So this will cancel this, and I'm left with phi now. So you see, we started from the second derivative. We started from the second derivative. I integrate it. So the integral will downgrade the derivative. We started from second derivative, downgrade to first derivative. First derivative, we downgrade to the original function phi. Okay, so this is what I mean by downgrading the integral. Okay, so it might not be clear to you when to use this, but as we go through the question, I'll bring it up when to use this. Okay, so you only use the above three formulas when you cannot use integration to directly downgrade the derivative. So let's hop right into the question. So the question says to obtain the system of equations in the form of this right here. Okay. Take note that my notations will be slightly different from Professor Shu's notation. I'm using Professor Ang Wai-tiong's notations, okay? Okay, let's start. Okay, so this is a transient problem, right? Transient problem means now phi doesn't just change with space; it also changes with time. So originally we have this grid, right? Normally we have this grid. So let me just draw it out. Okay, normally we have this grid, but then now how's it different in a transient problem? In a transient problem, we don't only have this grid because the values of phi are not just stuck in time. Now they change with time. So we don't only have this grid. Now, this grid only occurs at time is equals to 0 initially. Okay, this is the initial grid. But then since it changes the time, now we have to look at other times. So this grid can now also occur at time equals to the next time step. Okay, the next time step. So this occurs at t equals to delta t. Okay, so it's not just fixed like that, like a static image. Now it changes the time, so we have to consider future times. Okay, so the simplest case is when we consider the next time step, which is at time equals to delta t. So let's copy down the governing equation and solve it. So the governing equation that they give us is this: rho c, partial t, partial temperature, partial t, equals to this. Now let's have a look and identify what this is. I mean what these terms are. Okay, so ddt here means this is a temporal term, and that's why we call it the transient problem. Normally we don't see this, right, in so far in the past tutorials, because those problems didn't change with time, so now it does. So this is the temporal term, and that's why we call it a transient problem. It changes with time. And then what is this? So we have a first derivative, second derivative. Second derivative with respect to space is the diffusion term or the conduction term. Okay, you can call it either way, conduction term. Okay, so that's just identifying the terms. Okay, so now the first thing you do in transient problems is integrate both sides with respect to time. Okay, integrate both sides with respect to time over the time step. Over one time step. So integrate this with respect to time. Okay, rho and c are constant. That's why I could just directly do like that instead of like this. And then integrate this. Okay, over the same time. Okay, with respect to time, with respect to time. Okay, so let's have a look at the left hand side. The left hand side is easy, right? Remember I said integrals are opposite of derivatives, so they can just downgrade. The integral can downgrade the derivative. So from the first derivative, we go back to the normal function. Okay, so this will cancel with the delta t. I mean the derivative, and we're only left with t. So what I get is rho c t, then the limits of the integral. Okay, now how do we deal with the right hand side? Okay, there's nothing to help us. What do I mean? You see, do you see any ddt on the right hand side? No, right? It's a conduction term. There's no ddt. This is with respect to x. This is with respect to x. Okay, so there's no delta t. So we cannot do this clean trick here where the integral will cancel with the derivative. So this is where you use this formula. Okay, one of these three formulas. And since this, okay, let's have a look. Okay, yeah. Notice that we are integrating with respect to time. So that means we're not going to use the third formula, right? Because this is integrating with respect to space. So we can forget about the third formula. Now, which of the two formulas do we need to use? Because the problem told us to use the implicit scheme. So we're going to use the implicit scheme formula, which is this one. Okay, so let us go ahead and use that. So, what did the implicit scheme say? The implicit scheme says to evaluate this integral, which is now, to evaluate this integral, what we do is take f evaluated at delta t times delta t. So let me say that 3 more times. Take f evaluated at delta t times delta t. Take f evaluated at delta t times delta t. Take f evaluated at delta t times delta t. Okay, so let's take a look. So who's my f now? My f is just this entire thing. Okay, so what we do is, so this is my f, correct? So we take f, which is this whole thing, evaluated at delta t, so we write it like this, evaluated at delta t, then times delta t. Okay, that's how you use the implicit scheme. So let me write down here as a annotation to help you understand when you go through your tutorials. This is the implicit scheme. Okay, I'm just gonna write it like implicit scheme. Okay, so we change this integral into this term, via the implicit scheme. Okay, so now let's have a look at how we solve this problem. Okay, so let's take a look at this. How we're gonna deal with this. So this is where you have to know a bit of notation. So T at delta T, okay, which is the future time, right? The temperature at the future time. We're going to symbolize this as T with a bracket of 1 at the top, okay? T at 1, okay? T at 1. This is the future time. So this is the future, let me write this, future T, okay? And what about T at 0? So T at 0, we're gonna symbolize it as, we're gonna denote this with T at 0. So this is the past T. Okay, so this is a bit of a nomenclature which I will use. Okay, so the T evaluated at delta T, I'm going to call it as T at 1. The T evaluated at 0, I'm going to call this as T at 0 or T0, T1, T0, okay? Or T naught. Sometimes I'll call it T naught. Okay, so if we evaluate this integral, it will be at T1 minus T0, and then on this side, okay, on this side, I'm gonna annotate it like this. So you see, it is this function evaluated at delta t, and anything I evaluate at delta t, I'm just gonna put this superscript 1. Okay, I'm gonna put this superscript 1. So you see, I'm just gonna copy down this thing, same thing, same thing. I'm gonna copy it down, but at t, I'll write this 1. Okay, this is how I transform this term into this term. Okay, I hope that's clear. It's just a notation, okay? Just a notation. Okay, what's the next step? Now we have to use the finite volume method. So the finite volume method states to integrate integrate over the control volume, right? Integrate over the control volume means you integrate with respect to x from small west to small east. Integrate this side also from small west to small east with respect to x. Okay? So now, what do? We have to integrate this side, right? So when you integrate this, you can distribute this integral with respect to this term and this term. Okay? So what I mean is instead of writing it like this, I can integrate this term west to east and this term west to east, both with respect to x. But how do we do this? You see, again, we cannot use the integration to downgrade the derivative. Okay? There's no ddx for us to, just say integral cancel with derivative. Okay, so again, since you cannot downgrade the derivative, let's go back up and use the formula. Okay, but first, let's take a look. We're integrating with respect to space. Okay, x refers to space. So, which of the three formulas that I showed above has space? So let's have a look. It's this formula. See, this formula, these two formulas are with respect to time. So we don't use that. We will use this formula. It's with respect to space. So f evaluated at a plus b over 2 times b minus a. So how are we going to apply this formula? So let's have a look. Let's draw a control volume. So the control volume is this standard template that I've always shown you. So p, small east, small west. This is all we need. Okay? We don't need big east, big west. So, see, we're going to integrate over this control volume, right? So, who's a, who is b, who is a plus b over 2? You see, A is this one, right? See, A is the left side, so W is the left side. Therefore, A is W. Okay, so we know that A is actually W. Then B is the right side, E is the right side. So B refers to small east. And then who is A plus B over 2? A plus B over 2 is in the direct center of between A and B, right? A plus B over 2 is the direct center of A and B. So who is the direct center of west and east? That will be P, right? Okay. So what I can do is, if I want to evaluate integral from west to east of t using this formula, this will become t of p, right? This means the central value of f. In this context, the central value of p, the central value of t at p will be tp, right? I hope you can understand that. And then what does b minus a refer to? B minus a refers to the length of the segment. And we've already known how long is this segment. It's always the delta x. Okay, delta x. So this will be times delta x. Okay, so the middle f times the segment. So that's why I take the middle t times the segment. And the middle occurs at p. That's why I write t subscript p. Okay, so this is the formula that we're going to use. So if you do that, you integrate this, this will be rho c. Okay, so since it's t1, I'll use t1 at p times delta x minus this one, t0 at p times delta x. Whoops, this is not d, it's supposed to be x, right? Okay, so this side is easy. Integrate with respect to x, but then I have a derivative. Integral and derivatives are opposites, so they cancel, okay? So this can cancel with this, and I only need to copy down the inside. Don't forget this delta t. So delta t, I'm going to move it to the front. Then I copy down this thing. Okay? And now I'll just directly sub in the limits of the integral. So first integral we need to evaluate is evaluate this at east minus evaluate this at evaluate the same thing at west. Okay? Yeah. Okay. And from here, we are stuck with all the terms with east and west. Yeah, correct, correct. So actually one further thing that I'm gonna do is I'm gonna integrate. No, I'm not gonna integrate. I'm gonna factorize out this k, okay, just for convenience. Just for convenience. And I'm gonna distribute this rho c to here and to here. So what I'll get is rho c delta x and this is a bit unnecessary, but in the solution they did this. I'm gonna move delta t to the other side. Okay, so times delta t will become divided by delta t. So what you get is rho c delta x over delta t. And then again for this side. Okay, copy everything down. Okay, so we're gonna be using this equation a lot. So let's call this equation star. Okay, now we're gonna have to solve this differential equation at the internal nodes first. So at the internal nodes, we have nodes 2, 3, and 4. We have the general template, east, west, east, west. Okay, so now let's reuse. equation star. Okay, so let me just copy this directly. Okay. Take note that this line is at t equals to delta t. Okay, and with that, we need to approximate for these derivatives, which is just the central differencing scheme, which we are very familiar with. Okay, so we want to find this term. So the derivative evaluated at small e's. So we stand at small e's. So we take immediate right minus the immediate left divided by the segment. So the immediate right is phi e. And since this occurs at t equals to delta t, this is not just phi e, but it's phi e 1. Okay, remember this is happening at the future time, so we need to indicate it with this 1. Then this side, the immediate left is at um phi p, but also at 1. Okay, and the length of the segment is just delta x. This is delta x. Okay, so that means, sorry, it's not phi, because this problem involves temperature, right? So it's not phi, it's t. Okay, it's t. So d phi dt d temperature dx at e. Yeah, is equal to the future east temperature minus the future p temperature divided by delta x. Okay, then we also had to find the same thing but at the west. Okay, now if you want to evaluate this derivative at west, we stand at west, take immediate right minus immediate left divided by the segment. So immediate right is t p but occurring at the future, and is t big W occurring at the future. Then this segment is just same thing, delta x. Okay, so we have TP PW over delta x. Okay, now we substitute these values into the equation here and here. Okay, so let's go ahead and do that. So this whole thing, I'm just going to copy it wholesale. And the rest of it, I need to substitute in the value that we got. Okay, so after the approximation, we got this. Okay, now what we can do is we shall factorize this and simplify the numerator at the top here. Okay, so again, copy this wholesale and factorize out delta x. Then we simplify the denominator. So minus 1 is minus 2. So minus 2 tp in the future. And then minus minus is plus. Okay. Next thing I'm going to do is I'm going to distribute this k delta x to each term. Again, let's spit this back out. Okay. Yeah, so, okay. Now I'm going to arrange it in the form that we are required. So I'm going to arrange it in this form. Okay. The notation I use is different because Professor Shu, he omits the bracket one. Okay. He omits this bracket one, but I included it. Okay. So wherever you see there's a no superscript, no superscript, this actually implies that it's actually one. So actually it's supposed to be one, one, one. Okay. So let's rearrange it in this form that they require from us. So let's rearrange it. So first we want the T1P terms, so T1P terms, T1P terms. So you put them all together, you should get this. Then next we have the T naught P terms, so T naught P. So it's just that T naught. Yeah, just like this. So this is the equations for 2, 3, and 4. Okay, so this is the equations for points 2, points 3, and point 4. Okay, now we move on to the first boundary. So at point 1, let's draw this n. So remember this again occurs at t at delta t. This is point 1, this is point 2. Then we have the general template. Okay, so this is p, this is e, this is small east, and oh, this is small west. Okay. Okay. So again, we need to reuse equation star, reuse star. Let's go ahead and recopy that equation. Where's equation star? Okay, this is equation star. Okay. So we need to find again this term and this term, an approximation for these two terms. So how are we going to do with that? So let's have a look at the derivative at e. So let's take a look. The derivative at e, just take immediate right minus immediate left divided by the segment. So the immediate right is T1e, the immediate left is T1p, and the segment is delta x. Okay, delta x, this whole thing is delta x. So that means at east will be, okay, so the immediate right minus the immediate left divided by the segment. Okay, and the boundary, okay, sorry. So how are we going to deal with this term? Okay, so before we go ahead and take the immediate right minus immediate left, notice that this occurs at W. Okay, this occurs at W. So W is the boundary node. Remember, it happens at the very end of the domain. So this is the boundary node. And let's check if there are any boundary conditions we can exploit. So if you go back up to the question, okay, no. But if you look at the question paper, okay, if you take a look at the question paper, they told us that at that end, okay, at that boundary. So let me just write down what they say. By the boundary condition, they told us delta t one, delta t. Yeah. The first derivative at that end is zero. Okay, you can go back to the question paper and have a look. It says that the first derivative at that end is zero. So this is what we're gonna use. By the boundary condition, we don't need to do the immediate right minus immediate left. They've already told us what is the first derivative, and it's just zero. Okay, they already told us that the first derivative at the boundary is just zero. So we're gonna straight away plug in zero into this term. Okay, so now we can plug these two things into this, and we shall continue simplifying this equation. So, okay, so continuing the equation, now we're going to substitute our results in. So if you substitute, we have this. Okay, now we're going to substitute this. So T1E minus T1P. Okay, and remember, this is just 0. So minus 0. Okay, now same thing, just continue simplifying. I'm going to factorize out delta x. And then distribute it to each of these terms. Okay, then I'm gonna rearrange it in the general form that they want us, right? Arrange it in this form. Okay, so let's go ahead and do that. So we want the T1P terms first. So T1P, T1P, bring them together. Plus J delta X. Next, we want the T naught P terms. So just bring this to the other side. Next, we want the last term. And there you have it. Okay, the equation at the first boundary. Now we move on to the next boundary, which is at 0.5. Okay. So same thing. First thing first, we draw the sketch. We draw the sketch. So this B is 5, this is 4. Then we draw the general template. So this is uh okay, this is P. This is small e, small west, and this is big W. Okay. Then we're gonna reuse star. Reuse equation star. Let's go ahead and reuse that. Okay, so now we need to find approximations for these two derivatives. So let's have a look. So we want the first derivative at east, right? So we want dt1 dx evaluated at e. So we stand at e, then we take immediate right minus immediate left. But the thing is, we don't have the immediate right. So what we're going to do is we're going to use the point itself. Okay, so instead of immediate right, we're going to use the point itself. So the point itself minus the immediate left divided by the segment, which is delta x over 2. Okay, so the point itself is T1E minus the immediate left is T1P. Okay, T1P divided by delta x over 2. Okay, you want to simplify this. You multiply the top and bottom by 2. The 2 can cancel. Then we distribute the 2 at the top. So we have this thing at east is equals to 2. Okay. But if you have a look at the question paper, right? Okay, so notice that we're dealing with E right now, and E is the boundary node because it happens at the other end of the domain. So this is the boundary. that means we're expected to use a boundary condition. So what did the boundary condition told us? They say the boundary condition told us that the temperature at here is equal to 0. So they told us the boundary condition states T1 E is equal to 0. So that means I can substitute this to be 0. Okay, and therefore I simplify it to become negative 2 Tp, like so. Okay, and now we have to deal with the other derivative. So let's have a look. Okay, so let's look. To deal with this, we want to evaluate it at the west, right? So you stand at small west. Okay, so to find the derivative, it is immediate right minus the immediate left divided by the segment. Immediate right minus the immediate left divided by this full segment, which is delta x. So the immediate right is T1P, and the immediate left is T1 big W divided by delta x. Okay, now we can substitute these two results into our differential equation. Okay, substitute it here and here. Again, copy this first. So check. Yeah, so minus 2 T1P over delta x minus P. Okay. Again, okay, let me deal with this side first. Okay, good. Okay. Gonna factorize out delta x from the bottom. Then I'm gonna simplify the numerator. So we have minus 2 minus 1 becoming minus 3. Okay, minus 2 minus 1 becomes minus 3. Then minus minus becomes plus. Yeah. Okay, good. Now I'm gonna expand to these two terms. Okay, and now I'm gonna rearrange it in the form that they require from us. So first, the T1P terms. Okay, so this is T1P term, and this is another T1P term. Factorize out T1P. Next, they want the T not P terms. So this is the only T not P term. So bring it to the other side. And lastly, they want the remaining term. Okay, so if you check in the solution that they provided, they have a TB term, right? But why don't I have a TB term? Well, it's because they've already told us that the boundary condition is TB is equals to 0. So when you sub in TB equals to 0, it just disappears. That's why I don't have a TB term. And I already substituted, right? I already substituted up in the here. Here. Uh, this is where I substitute in. That's why it disappears and you don't see it there. Okay. But in the solution, they left it. They didn't substitute it in. But yeah, this is the right. Okay. So this ends our mini series in computational fluid dynamics. I hope you enjoyed this mini series on computational fluid dynamics. consider it as my gift for 200 subscribers. And it still amazes me that I can garner this much support. Okay? It's been a long way since I started this channel, and I never imagined I would have garnered this much traction. So, thank you. Your support means the world to me. If you found this mini series on CFD to be helpful, be sure to support me on Ko-fi or Payla to help the channel grow. Thank you.